Hello. Last but not least, at stage 7 is Borislav Stanimirov. Borislav has been a professional C++ programmer since 2002 and a game programmer since 2006. He has worked at Masthead Studios on Earthrise in Gameloft and in several startups, including Chobo Labs on Mayhem. His interests include low-level programming, optimizations, programming languages, and software architecture and design. Not many people know that Borislav is a fan of science fiction, and he's going to share some of it with us today. So, a round of applause.
Thank you. Business logic back to C++, science fiction, right? So, in 1972, Dennis Ritchie created C, and it was based on B, which itself was based on BCPL, but C was based on B, the programming language B. Anyone heard of it? Okay, so sure. Then in 1994, Bjarne Stroustrup created C++, and it was based on C. The thing is that if Dennis Ritchie had been, I don't know, content with B, then Bjarne would have created the language B++, and I would have had a much nicer alliteration today, bringing business logic back to B++ now. Sounds great, doesn't it? But we don't have that. Thanks, Dennis. So hi, I'm Borislav, and you can find these slides over here if you want to follow them on your phones or mobile devices, is.gd/bbb2cpp. BPP? No, okay. You can swipe on the screen for back and forth. I come from Bulgaria, and who of you knew where Bulgaria was before seeing the map? Anyone been to Bulgaria? Ooh. Okay, I saw a guy raise his hand the second time, so he has been to Bulgaria, but he doesn't know where it is. Cool. I'm mostly a C++ programmer. I'm mostly a game programmer, as you know. I also do a lot of open source. You can follow me at GitHub over there. And this talk is basically a state of the world talk. We're talking what there is, what there was being developed right now, what's going to be developed in the near future, and possibly the far future, about business logic. But what is business logic? Speaking formally, business logic is, so let me read this, a part of a program which deals with the real-world rules that determine how data is obtained, stored, and processed. Okay, that's too complicated. We'll deal with something simple. Business logic is the part of a program which deals with the software's purpose. So, in this program, its purpose is to add 2 integers. So, adding 2 integers is the business logic behind this program, and it's situated here, in this part of the program. Now, if you had a Java programmer write the program, he probably could have done something like this. But again, the business logic is still there, adding 2 integers. The rest of the program, which is not concerned with business logic, could be presentation, I/O, optimization, perhaps, stuff like this. But you can say that the program is composed of a business logic part and a non-business logic part. Now, business logic sometimes is complex. And when I say business logic from now on, I will only refer to complex business logic. I won't be talking about adding 2 integers. And you know what this is? This is a ray-traced image. So a complex software doesn't necessarily mean complex business logic. As some of you might know or might suspect, ray tracer is not a simple piece of software. It's pretty complex. But the business logic behind the ray tracer is actually relatively simple. So for each pixel of the screen or the image that you need to create, you cast a ray to the scene, then when it meets an object, you reflect or refract the ray, then trace it to a light source, and then trace it back to determine the actual color based on the reflections and the refractions. So that's basically simple, right? If we had a budget of, I don't know, say several hours to produce this image from our program, then I put forward this. Most of you, if not every one of you, would be able to create a program which does that in, I don't know, a couple of days. And if you have absolutely no experience with linear algebra and analytic geometry, then I don't know, a couple of weeks tops. The complex part in ray tracers is not the business logic. It's typically, for example, the optimization that lies behind it. Because nowadays, we have real-time ray tracing. So some people are doing this like 60 times per second. So this is pretty complex. Optimizing this, having heterogeneous programming, having all kinds of investment towards the performance for this could be pretty complex. But the business logic is pretty straightforward. Now this, you know what this is? It's Facebook, right? So I put forward this. If you had a couple of hours to create this image, it will take you probably years of coding on your own to create the entire software, which is Facebook. And Facebook has complex business logic. Anyone know what this is? Civilization 6. Okay. Any Civ fans here? I am one. Okay, cool. So again, some games, though not all, like some games like strategies or RPGs, they have pretty complex business logic. A lot of effort is put into creating the balance, the relationships between different objects. This is pretty complex. Anyone know what this is? This is Blender. And Blender is a CAD tool. And again, complex business logic. It will take you many years to create the business logic behind this. And anyone know what this is? It's Microsoft Project, the best software ever, of course. So yeah, again, certain enterprise software also has pretty complex business logic behind it, even though looking at it, you wouldn't say so. Now, this is much less fancy than our balls from the ray tracer example. Anyway, so what do we have here? Like certain languages are more popular with certain types of software. For example, for websites, we have nowadays JavaScript, of course, with Node.js and everything, but also C# for the backend, Java, Ruby. We don't have PHP, but we used to have it. But who am I kidding? We also have PHP, of course. Everyone uses PHP, right? So in gameplay for games, certain languages are popular, like Lua, for example, Python, C# too. And for CAD systems, like Python is used for Blender, but many other languages are used in many other CAD systems. For example, Autodesk Maya has MayaScript, Max has MaxScript, so yeah. And enterprise, again, is typically Java land, but also many other languages are employed in creating enterprise software, but notably not C++. And people kind of don't seem to want to write complex business logic in C++. And that's not to say that those software don't feature any C++ in them. Even browser, for example, you can view the browser as a C or C++ core, the browser itself, and for example, the JavaScript engine, which runs other languages which are used to visualize the websites. So you have, typically in most software, you have a core in a fast language like C or C++, and business logic written in another language. That's a very popular pattern. And this business logic is typically not written in C++. And in fact, the vast majority of cases, business logic is not written in C++ these days, I should say. That didn't used to be the case in the 90s. And so you might ask, what's the problem with that? Is there a problem with that? And the title of my talk implies that there probably is a problem with that. So, for example, the code is slower. Even with JIT-compiled languages like JavaScript or Lua, 2 to 3 to 5 times slower is the norm. Now, there are edge cases in which JavaScript or Lua can outperform naively written C++, but the typical case, the norm, is like 2 to 5 times slower. And there are the opposite edge cases, which naively written JavaScript can be tens of times slower than naively written C++. Of course, having a language running alongside C++, you will need some kind of a binding layer. This is a piece of software, oftentimes of significant size, which is used strictly for the communication between the two languages. So more software means more complexity, more bugs, more things to support. And of course, even with the best of intentions, there are bound to be duplicated functionalities. Especially for small utility functions, it's oftentimes, well, it's almost always not practical enough to have them exposed through the binding layer, but instead people write them multiple times in multiple languages. And multiple languages, multiple functionality, multiple times the same functionality, of course, means duplicated bugs. So why don't people use C++? And there are many reasons, and one of those reasons is that C++ does not have good OOP, and that's very controversial. I know. In fact, tomorrow we're going to have a talk right here on in this conference which says OOP is dead. And go and visit it. I'm sure it's great. But OOP has had a lot of criticism. And one of the main criticisms of OOP is that if you want a banana, you can get it, but with it you also get the gorilla and the jungle. So basically with OOP, people say that you want something simple, but you end up having a lot of complexity in your software. Also, people say that it dangerously couples the data with the functionality. And by that, they mean that imagine a class, and the class typically has some fields and some methods, and the fields and the methods reside in the same place, and it's not a good, I don't know. When we're talking about object-oriented programming, we're typically talking about stuff like loose coupling, but coupling the data with the functionality in certain cases can be a bad idea. Also, back in the early 90s when OOP was all the rage, people were saying, well, this is the future. You will write something once, one component, and you will reuse it everywhere else. Delphi programmers try to do that, but where's Delphi now? Anyone written Delphi here? Oh, quite a few hands. So it's not reusable. So it simply doesn't work. It's not as reusable as advertised, I guess. And most of all, it's slow. And this is true. Now, object-oriented programming is typically associated with dynamic polymorphism. And dynamic polymorphism is in the category of things which are slow and don't have good compilation errors, which is, I know, the exact opposite of modern C++. Modern C++ is focused in metaprogramming, in static polymorphism, basically in ways to get better compilation errors and better performance. So perhaps that's why a lot of people, a lot of C++ programmers at least, have forgotten or deliberately chosen to forget that C++ is, among other things, an OOP language. Now, in defense, many criticisms of OOP target concrete implementations. And I'm looking at you, Java. But if you come to think of it, like vanilla C++ is not much better than Java in object-oriented programming. Now, many are about misuse of OOP, like somebody was trying to fix a bug or trying to get into a new piece of software, and they made some horrendous misuse of object-oriented programming, and they misdirected their frustration towards the idea as a whole. And you can see quite a lot of these cases. I saw this terrible thing written in OOP, therefore OOP is terrible. And, of course, some are about misconceptions. I mentioned the promise of reuse, which didn't quite turn out to be true. So a lot of criticism of OOP has come from people not understanding what it's for and what it's supposed to be. But most importantly, software is written by human beings. And this is still true until we get some kind of a machine learning, VR on the blockchain, buzzwordy thing that will write software for us, but we still write software. And human beings think in terms of objects. And remember when now human beings are evolved in a world of objects, and they think in terms of objects, and my first formal definition of business logic was representation of real-world phenomena or real-world relations in our code. And the real world, you know what there is in the real world? Well, objects. And that's why we're good at thinking about objects. That's why every significant piece of human thought has had some kind of an object model behind it. Think about atoms. Atoms aren't balls, but in certain cases, it's useful to think about atoms as balls. So we think about objects, and in certain cases, this gives us greater insight in something. In order to have something very complex, like the business logic of certain pieces of software, we need to have objects in order to be able to process them as human beings. So, and if you come to think of it in fields which are dominated by business logic, like websites, certain games, also CAD, enterprise, the languages which dominate there, most of them, at least, are object-oriented ones. So, I'm going to give a few examples of powerful OOP, of powerful object-oriented programming, which is present in other languages, but not obviously present in C++. So, here we have a classic example of dynamic polymorphism with object-oriented programming in JavaScript. So you have your two, well, classes are functions. Everything is a function in JavaScript, right? So two functions / classes. If you don't know JavaScript, just think of those as classes. You have another function which can take anything, and everything that has a draw method will be a valid parameter to this function. So, of course, our square and circle are valid parameters to this function. And this is a typical textbook example. You can find it in any textbook dealing with OOP and object-oriented and dynamic polymorphism. The same thing in vanilla C++. So this is another thing that you can find in any C++ textbook. You have your interface class with a pure virtual method, draw, and, you have your square and your circle, you have your function, and everything works. I don't need to get into details, you know this. So, the thing is that object-oriented programming, as I mentioned, isn't modern C++. But C++ is a pretty powerful language. So, what can we have that will make this better? If you don't see any problems with it, I'll go on. So, there are polymorphic type-erasure wrappers. So, these feature a somewhat ancient library like Boost type-erasure and more modern ones like Dino and Folly Poly, which is by Facebook, part of the Folly library is by Facebook. And Boost is in square brackets here because Boost T, which also means type-erasure, is not part of the Boost libraries yet. So they basically allow you to do something like this. And I'm focused on this line over here. Now, all of the libraries have very similar functionality. And with most of them, you can create a macro like this, called library magic. So basically, that's true for all of them. So library magic basically creates a type based on an interface. Then you can have classes which correspond to that interface. And then you can use them in a function which takes the created type. So note that neither square nor circle are inherited from shape. Now, this is much more powerful because we can have existing classes which are unrelated to our previously created interface. And we can just, if they correspond to the following interface, we can just use them as intended. We can just give them to this function. Something which is nearly impossible in C++ is to have a runtime polymorphic function which requires the size of an object and can take a vector or a list because both std vector and std list have size, right? But imagine this in a runtime polymorphic scenario. Now, another example of powerful OP is if we continue with our JavaScript example, we can add functions to the existing classes. For example, we want to calculate the area. So we can create area functions for our squares and circles, and it will magically work. Now, imagining we have a side and radius, side for squares and radius for circles. What can we do in C++ to have this? Now, in vanilla C++, we can just open the definitions of the classes and write those functions in, which is not very useful. Not always it is the case that we can do that. And even if we can, this will, in a huge project, this will lead to a recompilation of the entire project, which we know can be a pretty cumbersome thing. And also, we might want to need it. We might need this in a single file or something, or in a couple of files. So here come open methods. Open methods. Now, this is not to be confused with unified call syntax. These are open polymorphic methods. Now, boost, square brackets, boost, not actual boost. T and a yom to the library, they allow you to create this in C++. So basically, you have your declare and define macros, which do some library magic and allow you to add methods to existing classes, polymorphic methods. So if you notice the virtual part here on the first line, that says that this is a method called area, which returns a double, and it's virtual based on the argument called shape. So because we don't have actual unified call syntax, in the last line over there, we have to use it as the argument of the function instead of ptr.area or ptr arrow area. But the first argument of the function is basically the object for which this is a polymorphic method. But note this, we created a polymorphic method with runtime polymorphism without actually touching the object. So we can do this in a single file, and for this single file, our squares and circles will have the area method without actually writing anything in the actual class definitions. This is great. People writing object-oriented code are used to writing stuff like this. People writing business logic want to do this because certain parts of their code are focused on certain business logic aspects of the software. Another example. Anyone know what this is? Yeah, right. Now, Perl is a write-only language, but this time we'll try to read some Perl. You know what else, though? There's this saying that behind every Python program, there hides a single liner in Perl. So, trade-offs. Anyway, so Perl has pattern matching, and with pattern matching and Perl 6, you can basically achieve this kind of magic, and the collide function is often given as the example for what I'm going to tell you next, as the motivating example behind this. So we can have collide functions having different, like arguments of different types. And we can define collide functions for different combinations of arguments. And then, based on what we call the collide function with, the appropriate one gets called. So you might think of this as function overloading. And you'll be right. This is oftentimes called function overloading in Perl. But the thing is, Perl is a dynamic language. It doesn't get compiled. So getRandomShape and getRandomShape, if we were to write this in C++, would return shape. So function overloading is a static polymorphism thing, and it wouldn't be able to work because shape has erased the type of the actual underlying class. So what if you want to write this in C++? We want to have a collide function which can tell us whether two shapes of ours collide. So we can do this. Basically, we can have a shape which has the collide function which we're going to use, then we can have an implementation. So in the implementation of every class inherited from shape, we need to have this function which is highlighted here, basically copied. It transfers the knowledge, like it calls itself as the second, itself strongly typed self as the second as the argument of the function, in order to have the implementation function be properly dispatched. So basically, when we have this requirement, we can solve it through two virtual calls and a significant amount of code, but it can work. That's what basically we need to do in vanilla C++. You get it, right? Everything cool? So, and you see, getRandomShape, it just returns a shape. It doesn't return the actual type, so function overloading would do us no help here. Yeah, that's the use over there, and it works. It will work appropriately. This is called multiple dispatch. Now, multiple dispatch is basically this. You can have a virtual function, but instead of being virtual over one argument, or in typical C++ or Java thinking, over the actual class from which this function is a method, it can be virtual based on many of their arguments. Now, this can be, as you see, mimicked with a couple of virtual calls and a significant amount of code. And it's basically exponentially proportional to the number of virtual arguments you need to write. So, for example, for 2, you need 2 virtual calls. For 3, you will need 3 virtual calls, etc., etc. You can think of this as like this. If you, for a typical virtual function, you have a virtual table in the class. And when you call the function, with indexing, it finds the actual function in the virtual table of the class. But what if we had a virtual table per function? And what if it wasn't a single dimensional array, but, for example, a matrix of n dimensions, depending on how many of the arguments are virtual? And if our types have some kind of IDs, we can, calling a function based on the IDs of the runtime IDs of the actual types, we can find the appropriate function in the matrix. So that's roughly, or that's the idea behind it. It doesn't, those libraries don't actually do that. Now, this is YOM code, the code typical for the YOM library. And notice how in the declare function at the top, we have virtual on 2 arguments. So this is a function virtual on 2 arguments. We can create our collide functions, and it will work as intended. So this is, again, something that certain cases, in certain cases, people might want something like this. And there's another example. This here is Ruby. And Ruby is one of my favorite languages because it's beautiful, but abysmally slow. Now, in certain cases, a Ruby program is tens of thousands of times slower than its C++ counterpart. But it's so beautiful that nothing else matters. So in this case, we have an imaginary game. And in this game, we have flying creatures. And one of the flying creatures can move to like creatures in our game can move to certain parts of the world. The world is composed of numbers. So if it can move to this part of the world, it can fly to there, and otherwise it cannot fly to there if it can. But this is a flying creature, so flying creatures don't care. They fly everywhere. This function always returns true. But also we have this thing, and I'm going to say what it is in a while. Afraid of events. They're called modules here, but OK, we'll see what we're talking about. So it has the can move to function. If it's afraid of evens, so it will return false if the parameter is an even number. Now we can create an object in Ruby. Then we can extend it with a flying creature. And it will readily move to 10. But if we extend it with the same object with afraid of evens, the can move to from afraid of evens will override the can move to from flying creature, and now we will have an object which can fly to certain places, but it will refuse to fly to an even number. And this here is basically an entire valid Ruby program. You don't need to have anything else, anything specific, any imports or anything, in order to have this running in Ruby. What can we do in C++ to have this? And I had this lecture, which was a full-hour talk of starting with this example and then trying different things in C++ until I reached what I needed. But one of the things at the very end was this. And this is called the interface to component pattern. And it's employed in actually a lot of projects. So we can have an object which has pointers to interfaces, and the interface is basically the name of the function. So you will need to have interfaces which have these functions as pure virtual ones for each and every function of yours. So, then you can extend the object, much like in the Ruby example, with certain instances of this object. And note that, like here, we're extending with flying creature and afraid of evens. And if you go back, you can see that extend with creature actually covers 2 of the interfaces we need. So extend with creature will set the creature as to point to can move to and move to. And extend with can move to or movement, say, it should be movement. That's a mistake of mine. Anyway, it will only change one of the pointers. So basically, each and every object has a virtual table of sorts based on these shared pointers. Now, this is very slow in terms of runtime. It features a lot of code on the part of the programmer, but it works. Basically, you can have the same code in C++ as you did in Ruby. And here's another example of a library that shameless self-plug I've written. And much like the Ruby example, this is on the entire thing. Now, I don't have the includes, but if you include dynamics and IO stream in this example, it will compile. It's a self-contained example with everything, which does the exact same thing. So what we had in Ruby were called Mixins. And the way to create classes out of Mixins is known to people in C++, but in a static example, in a static CRTP example. So these things over here are dynamic mixins. So with dynamics, you can have mixins. Like first of all, we can have messages, which are the interface, much like what we had in Ruby. So you declare there are pieces of interface called like this, like move to and can move to. And you see you have the arity as an argument. You don't need to have that, but I typically use it because it's easier for Visual Studio to give me better suggestions in code completion. Anyway, so then in flying creature, you can refer to the owned object via the dm this macro. So instead of writing this, you write dm this, and this is the object that owns you. Then you can create the mixin, and you can say that it responds to the move to and the can move to messages. So this is the interface with which it will contribute to the object. Then for afraid of events, you can do the same thing, but you can set a higher priority for can move to. So when you add flying creature, the object will rarely move to 10 because it will respond to move to. But when you add afraid of events, it will, much like in the Ruby example, because of the higher priority, it will override the existing implementation inside, and it will do the same thing. This is quite popular to do in many object-oriented examples. Composing and mutating, and basically composing and mutating objects at runtime, polymorphic objects at runtime. And this C++ library allows you to do so. And I have a small example here, which is a game. And it's not an actual playable game, but more of a demo, I guess. So I move those characters with my arrows, the arrows on my keyboard. So now this is an RPG, right? So in RPGs, we typically want to have like health bars over the heads of our characters, but we don't in this case. So we can write a health bar class, which can draw itself appropriately. And here, in the rendering system part, we can uncomment this piece of code or write it ourselves if we just wrote the health bar. So what does it say? If an object implements the health points message and has a health bar and doesn't have a health bar, we can mutate the health bar in. That's basically it. So now, if we run, and health bar is a class that I've written previously, our objects have health bars. Now, why don't we check, like, if you see the opposite, the lines before that. If the object has character, we add character rendering, and this can also tell us that the game has this gameplay absolutely decomposed from the presentation. But if we have a character, we add character rendering. But if it implements health points, we add a health bar, because not only characters have health points in our game. We can have like crates, destructible objects, stuff like that. What else? We want to distinguish between different players, between different characters, between the teams of the different characters. So we can add some more lines here, like if the object is a character and it's from team 1, we can add a circle underneath, which is red, or otherwise add a circle underneath, which is blue. And it will work. But there's also another thing which we have, and those are mutation rules. So again, only having the actual circles and having a mutation rule. This is the bundle mutation rule, which tells us this: if we add a mixin, it also adds the others from the bundle, and if we remove a mixin, it removes the others from the bundle. But we can run this, and we see we have circles, but they're on top of our characters. So we can continue changing the code. So if we go to the selection mark, which is actually the circle that's being drawn, we see that it responds to supply rendering parts, but it's on top of the character. So this means it's called last. We want it to be called first. So we can add a priority, and the higher the priority, the earlier something will get called. So you can also notice that we're talking about multicast here, but if we add a priority, it will get called first, then the character will be drawn, then the health bar, and again we have a working thing. So what I want to show with this is that with minimal changes in the code, minimal changes in terms of how many places you're touching, you can have great additions and great changes to the actual software, which is something that's typical for business logic code. Now, another thing that we have that we don't typically have in C++, but we do have in business logic programs, the ones that I mentioned, is Hotswap. And Hotswap means basically changing code in your program while it's running. So changing the behavior of the program by writing or changing existing code while it's running, so having it changed in the program somehow. And it's really easy to imagine how this will work in other languages. But this is typically a development feature. So when a project has Hotswap, it's typically used while the project is being developed. And for example, when you reach a certain part of the execution, you meet a bug, or you want to add some changes over there. So you basically make your changes. You see them being reloaded live instead of having to, say, replay the steps that you had to make in order to get there, instead of having to deal with terrible compilation times or deployment times. You just swap it as it's running. But I say typically, of course, plugins, stuff like that, it's basically the same thing, but in release, like in releases. Now, again, most business logic programmers are used to having something like this. They wouldn't even consider working without it. And Hotswap comes in two varieties, and the stateless one means that it only changes functionality. It doesn't actually touch the state of the software. And it's trivial in scripting languages, in dynamic languages. You just need to, since every dispatch in dynamic languages is made through late binding, you just need to reset the functions to point to something else, and they will do it. So that's typically made by you re-execute a certain script, and it will change the definitions of the given functions, and it will propagate in the entire software. The thing is that this is really easy to do in C or C++. We can do it through shared libraries. And who here does Hotswap when developing code? You should. It's trivial. I see 2 hands, maybe 3. The light is really bright. So you basically need to do this. It's a function pointer that you can get from a shared library, and when your shared library gets rebuilt, you can just add a file watch, and the file watch will see that it's rebuilt, and it will reload it and reload the function pointer, and you have a function which is hot swapped. This is trivial to do. You don't need anything more than that besides the file watcher, and we can all find an existing file watcher online. This is for Linux, like for Unix type of library, but for Windows, you can just, I don't know, you can use, instead of dlopen, load library, and instead of dlsim, find proc address, I guess. But the code is basically the same. You can even have a macro for those, and the code will remain the same. If we get back to the dynamics example, I have this class over here. This is stupid artificial intelligence. So if it can go left, it goes left. If it cannot go left, it tries to go right. And if it cannot go right, it basically harms itself in desperation. So right now I'm commanding both characters with my keyboard. What if I make a change? So let's say, OK, first of all, I need to load the plugin. So OK, I loaded it. And notice I'm moving one character with my keyboard, but the other goes left. Now there's a river. They can't go left, and they go right. And they keep moving back and forth. But what if I were to change this? So if you can't go left, then go left. And if you can't go left again, then harm yourself. And so note that I haven't stopped the program. It's in its previous state. So the state is untouched, but this is functionality only. So you see, I'm moving my character, and the other harms itself. The health bar is getting lower. So what I have here is basically a file watch, which watches a shared library. And when the shared library gets changed, which I just did, it just reloads it and changes the appropriate functionality. Now, this library in particular makes it very easy for you to have something like this. But with a minimal amount of effort, you can make other stuff do hot swap in C++. Now, this is typically done for C interfaces. So what the previous code will work for functions which have a C interface, like their extern C functions. there are many libraries, and runtime compiled C++ is an example. If it is not a library, it's more of an example which you can try at home and basically play with different ways of hot swapping C++. And this time I'm talking about classes and stuff with the C++ binary interface, which wasn't my previous example. There are many other ways to do so, and I'm even working on an open source library which isn't out yet. But they basically look at your code, and based on your code, they create the magic underneath. So what you end up writing C++ classes, but it hides the C++ implementations in C binary interface functions and exposes those. You can do this manually, and in the wiki of runtime compiled C++, there are examples of other libraries which try to do that. Again, this is not a library. This is more of a toy for you to play with. Now, there's also something else, some other efforts in the same direction, which is hot patching, and Visual Studio has had this for many, many years. It's called edit and continue, and it doesn't work. So people have tried it, and for smaller projects, it does work. I'm sure that I can even hear a success story with edit and continue, and they're working on fixing it, but I'm not aware of anyone using edit and continue for bigger projects. Are there such people here? No, no, no. It has bad reputation, right? But Live++ is a library, or a software, I guess, which hot patches your C++ programs. And by hot patching, I mean this. You have your executable, you change some code, then the hot patcher software finds the changed code, compiles it, and rewrites the executable loaded in memory with the new assembly. So it has to add some jumps, has to add some reloading, but that's the gist of it. So Live++ is an example of this, but it's paid proprietary software. And there's the other thing. I mentioned about stateless Hotswap, which is, if not trivial, then relatively easy. Stateful Hotswap basically deals with swapping, which in some way changes the state. It could change the state, like add something to your world, but in most cases, you will change the format of the state. Like, for example, you add a new member to your character in your game. Like, say, you add mana points. Your characters used to have health points, but they now have mana points, and you want to hot swap this. So basically, what you need to do in this case is serialize the state, perform the hot swap like you did before, and then deserialize the state, taking care of the new format. Now, this is easy in dynamic languages, which have reflection. You can analyze the state, and based on what you reflect from the current state, you can basically serialize stuff. But this is hard on C++. The thing is that Clang plugins are getting more and more popular these days. And even though we don't yet have static reflection in C++, there are many, many Clang front-end, like LVM front-end for plugins for Clang, which can help you have at least the serialization part of the static reflection. So these are three, but there are many others in various stages of development. I think those three are the most advanced ones, but you can also try playing with Clang plugins yourself. And I propose that this is the future. Then we will be seeing more and more front-end LVM plugins for C++ and other languages too, which help you, I don't know, remix the language, create some kind of a dialect of yours, which will help you do your particular needs. But the thing is, you already have some serialization. You're writing software. This software typically needs to serialize its state in some way, whether it's on the network or to files. You most likely have implemented serialization in your own way, whether it's manually or with code generation or even with Clang plugins. This most likely exists in your software. It's typically, again, if not trivial, then at least easy to serialize your state, perform the hot swap and deserialize your state, and have some kind of versioning which will identify the difference of the format between the two states. I've been dealing with such types of code like since 2007. I've been working on various ways to hot swap code in C++ and in C without, whether it's stateless or stateful. I've been doing this for a long time, and I can tell you it's not that hard. It works. It wasn't my full time. Like, I've spent probably several months in the past 12 years doing something like this, and it just works. I encourage you to try it. Hotswapping in C++ is real. It's possible. It's been possible for years. People should use it. And one more thing. Remember what this number is? We're talking about things which make other languages more, which make them nicer than C++, which make people choose them instead of C++. Now, REPL. Do you know what a REPL is? Who here knows what REPL is? Okay, I see a couple of hands. Well, it means read, eval, print loop. So basically, it's an interactive environment which helps you, which you can start with your software, and you can write code in it, and it will get executed interactively while your code is running. Now, this is a bit similar to Hotswap, but also a bit different. So the idea behind it is that it can be used for creative stuff, like for prototyping and basically having minor changes while your software is running without actually having to go to the IDE, without having any particular idea. The creative part of it is probably key here. And again, since business logic is so huge in some projects, people need to have some kind of fast prototyping environment which helps them do that. For example, this here, what you're seeing right now, is a browser. My slides are HTML with JavaScript. So I can press F12, and I can see the browser console. This is for Google Chrome. So if I tap here, and then, oops, sorry, and go to inspect, I can see that this is a heading with the ID demo-h2. So, okay, I go to the console. Sorry. I forgot the name. What? Demo-h2, right? Okay, that's heading. So what can we do? It's called A, so A.inner text, say we can set it to something. And it changed. A.style, .color. And it works. And I'm doing this in my browser while this is running. So this is an example of REPL for the browser, but almost all scripting languages have some kind of a REPL. And people use it a lot. They use it especially for prototyping. So they open up their software on certain element or certain state, then they open up their REPLs and they start messing with the state however they want. And it works. And it's especially convenient for creative stuff and sometimes for bug fixing too. Imagine you can stop the game at, the software in some state where you observe a bug and you want to mess with the state to see what it's all about. You can just open your hypothetical REPL and you can inspect the state with commands of the language that you're using right now. And the question here is, can we have this in C++? Can you write code in the debugger? Can you add objects, calling stuff, calling functions? Well, yeah, you can call functions, for example, but can you write a new function? And well, okay, you can basically write stuff with your debugger, sure, and it will probably work, but having an interface for this, well, having it, I don't know, being callable and having the entirety of your language and being able to write new stuff in a way which gets represented immediately in your state, especially in a release mode, for example, without any debugging information or without having a debugger present. For example, you can ship this to users. Having an actual REPL, you can ship it to users or to people who don't necessarily write C++ code to write simple functions in your existing project while using your headers without having to expose this to another language. Because another case for people using languages besides C++ is to have some non-programmers basically write something in a DSL, because all of those languages typically have powerful DSL capabilities. Now, well, with debugger, I grant you, it is possible, but also there have been many efforts to have something like this in C++ while interpreting C++. So there are efforts in interpreting C++. CH and Cling are basically the only two alive now. There used to be many more. But CH is proprietary software. It's C++ interpreter. It's really fast, really easy to integrate. But there's a but. And Cling is basically a backend for Clang, which instead of producing executables or binaries, basically interprets it. Embedding CH is kind of easy, but embedding Cling is notoriously tough, and there have been many efforts to embed Cling like you would embed another scripting language within your project. And I don't know if any of them have been successful. I think most of them failed. You could go all in. If you go all in, that means that you have the entirety of your program being interpreted. Instead of compiling it, you just put it to the interpreter and go with this. And this can lead to some unexpected bonuses, like having most of the benefits of having a scripting language done, like everything will work, just like I advertised it will. But it will probably be slow, like really, really, really slow, because when you have a scripting language, it runs on a core of C or C++, which takes care of the part that needs to be fast. And in this case, you wouldn't have anything that is fast, even if it needs to be fast. And also imagine C++ is pretty hard to compile. So in a scripting scenario, you will have to do the effort of compilation basically every time you start the program. So there are steps you can do to avoid this, but typically this will be the case. So not very nice. Now, CH might sound appealing, but it doesn't support the entirety of C++. It basically supports C with classes. You could have templates inside of it, but they need to be like exposed externally. So it's a lot of effort to have any templates in CH. Now, there's another approach, and it's the hacky approach, what a friend of mine actually created. And it's basically this. You could have a shared library for each line of code you write in your REPL. So what I wrote in my example of the browser, you could have a shared library which you then load and execute each time you write some code. Now, in reality, it's a bit more complicated than this, but I won't get into details. What I'm talking about is RCRL, which means read, compile, run, loop. And Viktor Kirillov, who had a talk today, also has a talk about it. And again, it's not a library, it's a toy, which you can play with and basically have your have a go at creating a REPL for C++, reusing any parts of the code you want. So here is a host application, which has some squares rotating here and there. And we can add some code. We can compile and run it. This just some include, which we then have available. We can add some more code. So we're adding an object now. We can compile and run it. And if you see, oops, I want to hide the thing, but OK, so forget it. I won't hide it. Believe me, there's an object. You can see the bottom of the square at the center, the gray one. So what if I compile and run? You see it got white. So at the center, at the bottom, you have a white square rotating. So we can move the object and make it rotate faster, and see it works. We can also make a loop, and for all our objects, we can set the rotation to be a bit slower. So if we compile and run this, all objects start rotating more slowly. So that's basically it. And of course, it's much more powerful than this. It has its limitations. It's not a full-fledged REPL, but something pretty close can be achieved with C++ today. And of course, there's more. There's more for which I don't have the time. But for example, build time optimizations. And again, this friend of mine, Victor, he had a talk earlier today, who was to the build time optimizations talk. So I advise you to watch it. He has a list of a huge amount of resources which will help you deal with optimizing your build times, which is another thing C++ gets criticized a lot for, and which is another thing which deters people from using C++. People who write business logic are used to having things immediately, hence the Hotswap, the REPLs, the convenience of writing code. You can bring C++ really close to this. There's, of course, testing, and we've seen a lot of improvements in testing these days. There are many new libraries, many changes to those libraries. Basically, the ideas created by test-driven development, which were started in business logic software, are being put into C++ with greater and greater success. There's, of course, mocking, which is another thing the people writing business software use, which they use to mock parts of which are not concerned with their business logic. Or vice versa, it can be used to mock your business logic, so you can test, for example, your UI or your networking. And we don't yet have any of this in C++, but efforts are being made. You can check out libfuzzer, and many other Clang plugins exist, which can help you with property-based testing and fuzzing. Fuzzing is basically generating input for your program, so you can cover the most paths, the biggest amount of paths through your software possible. So basically, this can only happen if the fuzzer knows about your software. So typically, this is done by libraries which have, for languages which have reflection. And through this reflection, you can analyze what can be called, and then you call it with different arguments, like different values, and you can have fuzzing inside. So different inputs, and until you cover the most of your software paths. I'm going to finish with this. C++ has disappeared from the business logic scene, I guess, but as John said, the beast is back. Thank you.
Any questions?
So as you said, most of the languages used in business logic have all of those features out of the box. So how would you, well, I think it's hard to convince anybody to use something and, install some tools, add some macros, and so on, if you can just do this out with a language that has all of those out of the box.
Sure. Then, as we can see, a lot of software is written in different languages, paying the price of worse performance, of having to deal with the complexity of a binding layer. But there are cases in which people cannot pay the price. For example, Dynamics, the library I showed you, which deals with composing and mutating live objects in C++, has had a lot of real-world uses. And all of them were in mobile games, because mobile games, as opposed to desktop games, for example, are much less likely to sacrifice performance because the hardware they run on is much weaker than desktop games. So several mobile games were made using this library, basically for performance reasons. So yeah, indeed, starting something today and expecting all of the benefits of which business logic languages have out of the box in C++ isn't the case, hence the science fiction. But what I meant to show you is that it's not impossible to create, I don't know, an environment or a framework or parts of the framework which can be then combined into, I don't know, a development environment for C++ which has all of these features inside. The parts are already there. The combination isn't.
I don't see any. Okay. One moment.
Isn't the DL clause very dangerous for C++?
DL clause to be dangerous? I don't know how. DL clause basically
Like
frees the or dereferences the reference count of a shared library.
Yes, but it also like sometimes you have a pointer to a static value, and that value is distracted. So.
Oh yeah, yeah. Well, if the static library has introduced something into the state of your software, then you will have to deal with it. So that's it. But that doesn't necessarily have to be the case. For example, in Windows, it's even worse. In Windows, the allocation done in static libraries is done because they're globals. The H global has their own allocation space in the Windows virtual memory manager. So when you unload the library with close library, everything that has been dynamically allocated from there also gets deallocated, whether you want it or not. So you can have pointers to not static, but even like objects which were like vectors or members of vectors created by a static library, and they will suddenly disappear. So that's even worse. But again, if you know what you're doing, you can basically manage all of this. I have a lot of experience with this, and it's not a huge effort. I've worked on 3 different projects which all featured Hotswap of C++, complex C++, nonetheless, more. So it is possible. Yeah, you will shoot yourself in the foot a couple of times. You will learn from your mistakes, and it can be done.
So, Borislav, many thanks for your presentation. Everybody, many thanks for your attention and for attending first day of Code Dive. You're invited for a middle party at Mleczarnia at 7 p.m. And see you tomorrow on second day.